Thank you very much. We're very excited to be here today. So, do we have a laser pointer?
Yes.
Okay.
Doesn't look like one, but it's like.
Mouse. Laser pointer's more fun. Okay, all right, well, this will be fine. So, during the last century, there have been enormous changes in the coastal land area in Louisiana, mostly along the Mississippi River Delta. This figure is from the state's Coastal Protection and Restoration Authority, and it illustrates in red the land that is either already turned from land to water since 1932 or is projected to change to water by 2061 under effectively a worst case scenario for environmental conditions if no additional restoration projects are undertaken. So this sort of gives you a sense of the dire issue that we face. Now, there are other ways that you can look at land loss in a map sense. And one thing that, an approach that we've undertaken for a paper published last year, let's see, where's the mouse, is to map land loss as a function of the retreat of the shoreline. And so what we did in this particular paper is define, in this case, the shoreline as the boundary where 50% of the Earth's surface is land and 50% of the Earth's surface is water. And so when you look at different parts of the delta, the Mississippi River Delta, you see different results. So for example, in this case, the blue line represents the 2010 50-50 land-water ratio boundary. The white line represents the 1932 50-50 land-water boundary. And over here on the left-hand side of this figure, this is an area where we have a lot of active deltaic sedimentation. And you can see that the lines either fall right on top of each other, or in some cases the blue, sort of the more recent coastline, is pushing out into open water. So this tells us we're building land. In contrast, these more dormant sections of the delta that are receiving less sediment and are undergoing fairly rapid subsidence are showing very rapid coastal retreat rates of up to 200 meters per year. And the effect of this is to expose communities that may have had kilometers of land in front of them, to expose them more to marine forces such as hurricane surge. And the yellow dots that you see in this illustration show the locations of communities and coastal basins that I'll be referring to in a later graph. So what drives coastal land loss or gain in a river delta? Well, sediment supply is a big factor. Sediment retention, how much of the sediment that comes down a river is retained to build land. Global sea level rise and fall can either inundate or expose land. Ecosystem productivity, the production of plants builds soil volume and helps bind soil together. And then finally, subsidence, the process that we're going to be talking about mostly during this press conference, which the USGS defines as the settling or the sinking of land surface due to subsurface movement of earth materials. So along the same lines, what drives subsidence in the river delta? Sediment compaction is one. Glacial isostatic adjustment is another. This would be the response of the land surface to either the proximal or distant unloading from ice. Regional sediment loading. By piling up thick quantities of sand and mud, you can actually depress the Earth's crust. Salt dynamics operate in a similar kind of way. Fluid withdrawal. Water, petroleum, hydrocarbons, both fluids and gases. And also realignment of natural drainages that can encourage decomposition of the organic material that was built up in deltaic soils. And all of these processes take place at different temporal and spatial scales. And so figuring out, the total amount of subsidence that's occurring at one point in time and space is the sum of all these phenomena. So what are the implications for this? Well, we've seen that the coastal land margin is retreating rapidly towards inland. And so this figure shows, also from a paper we published last year, shows it's a graph of percent land growth from, or diminishment from 2002 to 2010 in the coastal parishes of Louisiana, and percent population change from 2000 to 2010 in the same time frame. And what I'd like to draw your attention to is overall, for part of the data set, there's a fairly distinct linear trend that shows that if you are gaining land, you can support a larger population. If you're losing land, you're probably going to lose population. And unless you are a community that's actually investing in flood control to prevent the impact or diminish the impact of things like hurricane surge, such as the catastrophic flooding from the ocean that we saw in parts of the 2017 hurricane season. And this brings up the point that that land loss, which in our case has a very strong component that Mead and Tor and Kathleen will talk about, driven by subsidence, presents an existential threat to coastal communities. And now I will turn it over to my colleague Tor from Tulane.
Thanks so much. Basically, this press conference is actually very timely because, as it happens, we earlier this year published what we call the new Subsidence Map for coastal Louisiana. The reference is up there in case you're interested in further details. It's a very short paper. It's only 2 pages. I will get back to this map at the end of this short presentation, but I want to give a little bit of background so you have a sense of how we were able to do this. And the key element is what is shown here, something known as the Coastwide Reference Monitoring System, which is a state-run program that covers the entire coastal zone in Louisiana by means of almost 400 monitoring sites. These sites are used to basically track environmental change across disciplines, looking at a variety of elements like water levels, vegetation, and so on. The one element that is key for our analysis is a device that measures changes in elevation and also accretion rates, and combining those things together, it's possible to calculate the rate of shallow subsidence that happens at each of these sites. This program has been up and running for a little bit over a decade, so we're essentially looking at what is happening in this zone today. I put up a few logos to highlight the fact that the Coastal Protection and Restoration Authority plays a big role in this. USGS oversees the whole data collection effort, which is a massive effort and is unparalleled anywhere in the world. All the data are publicly available, and that basically allowed us to do this analysis. In order to get to this subsidence map, you need a few additional things. So I'll start off to illustrate a little bit better how this elevation table marker horizon system works. You actually see a picture here of someone doing these measurements. It's a rod that is driven deep into the subsurface. Let's see if I can, it's sitting right here. The horizontal arm here is attached to this rod, and these vertical pins are dropped onto the wetland surface to measure elevations at the millimeter scale precision. So what happens is the site is revisited twice per year, and that way over time you can track how the surface is changing. As I mentioned, combine that with accretion measurements, you can derive from that the rate of shallow subsidence in the top, say, usually 20 meters. In order to track deeper subsidence, which also happens, as Sam just pointed out, we use data from GPS measurements that are not as abundant, but that is not a huge problem because the deeper subsidence component tends to be a little bit more constant across this coastal zone. There is definitely variation, but there is not as much variability as in the very shallow subsurface. So those two things together basically gives us the total subsidence rate as observed at the land surface. Now, if we want to take the next step and figure out how fast sea level is actually rising relative to this coastal zone, of course, we also have to add in sea level change as such, and those data come from satellite altimetry of sea level in the Gulf of Mexico. So adding those three things together, we can produce maps that look like this. So this is another earlier publication that came out last spring. And this is a large selection of these monitoring sites that I just pointed out. They're color-coded, and in this case, they show the rate of relative sea level rise. So that's the sum of those three components I just pointed out at each of these sites. You can see that there is some variation. We find some of the highest rates in the Mississippi Delta. They also tend to be a little bit higher near the coast than further inland. But there is also a lot of variation. The really important take-home message is this number. So the mean rate for this whole region is about 12 millimeters per year. Again, with quite a lot of variability from site to site. The significance of this number is that the global mean rate of sea level rise at this moment is about 3 millimeters per year. So we're basically looking at a region that is experiencing a rate of sea level rise that is 4 times higher than the global average. And again, that is largely the result of these rapid subsidence rates. So this is a map with a lot of dots, and that takes us back to the map I started off with. So the final step was to do an interpolation to basically make a continuous map. You see the little black dots, which are the monitoring sites. I added one note here to be interpreted with caution. The point is that because there is so much variation from one site to the next, this is really a map that should be looked at with, you should kind of squint your eyes and really look at the big picture. There are some trends that are worth pointing out, that in the far southwest corner, the rates seem to be a little bit lower, which is probably a real thing. The highest rates, they tend to occur closer to the coast, such as in the Birdfoot Delta, near the mouth of the river. The really important number is basically that mean number, which is about 9 millimeters per year. So that's basically a reasonable baseline number for what is happening in this region right now. And with that, I'll hand it over to Mead Allison.
Thank you. I'm Mead Allison from Tulane University here locally, as well as Tor and the Water Institute of the Gulf in Baton Rouge. And just to back up for a second and kind of fill in a couple of pieces from the excellent introduction that Sam and Tor gave. One of the things is that this is very closely linked to the state's master plan for coastal restoration and protection, right? So at the heart of the master plan lies a series of numerical models to test suites of restoration and protection projects for their viability and their ultimate value on the landscape. But what goes into those models are things like subsidence rates and relative sea level rise rates that for a large part define how viable these projects are going to be. So from that perspective, understanding a little bit better what the spatial and temporal variabilities and the mechanisms driving subsidence are in coastal Louisiana is hugely important to the state's effort to preserve what we have and restore certain areas. So there's that point. And then also, last year, a group of us, including folks up here, had a paper out in EOS, AGU. Allison's got a whole set of paper versions if you'd like a paper copy after this. But this really talks about, it's called Global Risks and Research Priorities for Coastal Subsidence. It's a result of several international workshops where we got the coastal subsidence community together and we talked about sort of what's a way forward, what are the risks, and how do we improve our understanding of subsidence as an issue. And so from the risk point of view, one of the things that's a take home of this is that what's going on in the Mississippi Delta, as this session is called, the canary in the coal mine, right, is that we're ahead of the curve in a negative way, right? The combination of changes we've made in the basin and changes we've made in the delta that have limited new sediment coming into the area, and the rapid subsidence rates we're seeing are together working towards making the situation, as Sam showed, desperate in terms of land loss. But this is something that is going to be common in deltas across the world and also in major cities due to different mechanisms. Sam was showing sort of a mix of mechanisms that are operative in cities where there's a lot of water and fluid withdrawal, accelerating subsidence rates in coastal cities. So anyway, those are two issues I think that are important to kind of give a little more perspective. But what I want to talk about briefly is and both Kathleen and I are really going to talk about kind of what's the future, what came out of these workshops, what's sort of a way forward scientifically to improve our understanding of subsidence in systems like the Mississippi Delta. So this is a group of scientists from a variety of universities funded by the Army Corps of Engineers, who obviously, due to the navigation channel in the river and their flood protection systems, are very interested in the subsidence issue in coastal Louisiana. They funded an effort to develop what we're calling a Subsidence Superstation to tackle some of these things that Sam brought up. And so objectives, as I said, are you really want to test different ways to measure subsidence, right? The tough thing out there is it's not an easy thing to measure. It takes a period of time for many types of measurements to build up, like a tide gauge, a record of relative sea level change. And in some cases it's very expensive, as Tor said, putting out these kinds of networks and such. And so there's an exploration of how we can tackle this from an instrumentation point of view. And also compare different types of measurements of subsidence. And then finally, Kathleen's going to talk about sort of the remote sensing side of this, right? Because that's extremely appealing, the idea that you can get away from ground-based stations, and if you can make these measurements from satellite and airborne systems, and total elevation change of the ground surface, you really have a potential to develop maps that are very high quality to support some of these efforts at protection and restoration. So, and then the idea I think that Sam put forward is that there are a variety of mechanisms operating. They operate on different time scales, and they also operate over different depth scales of the sediment in the crustal column below it. And so understanding that mix of processes is really a vital step in order to develop multi-parameter numerical models of subsidence, right? Because that's another appealing way to go, is to say, I don't want to just rely on measurements. I'll use my measurements to calibrate a multi-parameter model, and I'll be able to predict in deltaic systems, knowing all the important first-order effects, what the subsidence rates will be across a delta. So the Superstation site was emplaced over about a year and a half ago. There was a sort of second phase of getting a little more instrumentation. So it's been about a year that the system is now fully operational in the Delta Plain. We selected a site at Myrtle Grove, Louisiana. As you can see, it's about halfway between the river mouth and the city of New Orleans. It's about a 45-minute drive south from here, in a natural wetland that is in a degraded and degrading state. One of the interesting things about this site is that this is an area that's proposed by the state of Louisiana to put a large sediment diversion from the Mississippi River. One of the building strategies of the state's master plan is to open holes in the levee system and reintroduce water and sediments and build out new deposits into these degraded basins. And so one of the things we were pushing to get this in place, and its site selection, was potentially this will have a record of subsidence in the area, and then after the diversion comes in and you start loading that area with sediments, we can actually get some sense about how that sediment loading will affect the subsidence rates, because that's really critical. When you look at the land building that's predicted for these diversions, it really comes down to not just how much new sediment they're putting out, but how much they to form the underlying surface that will determine the ultimate land building potential of these things. Okay, so what is the superstation? Well, it is at one of the CRIM sites that Tor just talked about, so it already has about an 8-year database of shallow subsidence rates at the site and vertical accretion rates. So we're within a couple of 100 meters of one of the CRIM sites. The first thing was done was a sediment boring. We really want to know what the sediment column looks like in this area before we decide where we want to place instruments. And what we found is that there's about a 40-meter thick, roughly 140-foot section of deltaic sediments that have been deposited since the delta began growing out in this section of the deltaic plain. So it's sitting right on that Pleistocene surface that's much, much older. And that's very important because if you're thinking about compaction, these greater aged Pleistocene sediments have a whole lot less potential to compact in the future because they're much stiffer already than the Holocene section. And so the ultimate selection for where to place the different components of the system was defined by the thickness of the Holocene. So there is one hole that goes to the base of the Holocene, basically one hole in the middle of the Holocene, and one up about 10 meters below the sediment surface. And each of these holes has a fiber optic strain meter or extensiometer that was developed by the Scripps group. And these are, I'll give you another picture here in a minute on my last slide of what they look like in detail. But basically the idea is to use a fiber optic cable that is anchored in the subsurface to that depth to effectively tell you how much subsidence is going on within that depth interval from the surface down to where that sensor is anchored. So effectively, we're seeing the subsidence rates over 3 different depth intervals, starting from 0 to 10 meters. Actually, it's a little below 0 because the instrument package is below the ground surface. The middle of the Holocene, and then take out the Holocene section, and what do the deeper processes look like? Now, the other thing is that these have continuously operating reference station GPSs on each one of the holes that are also anchored to those depths. So effectively, you get, for instance, in the 40-meter hole, the strain meter is giving you the subsidence from 0 to 40 meters, and the GPS antenna is giving you from 40 meters to the center of the Earth. And so you have a way of 6 different measurements that give you an idea of over what depths subsidence is occurring. The INSAR reflector thing just reflects the fact, bad pun, that INSAR, the radar remote sensing stuff that Kathleen is going to talk about, needs ground-based stations, and so this can effectively serve as a ground-based station to help reference that information. So here's my last slide. I don't have data for you yet. It takes a while to build up information. There are several posters here at AGU, and you can read the abstracts. Some of them are upcoming, some of them have already been done, that are about the superstation, and you can get a sense of some of the early data. But again, it's a timeline, and trying to piece out a long-term rate of subsidence in any one of these sensors, it takes a fair amount it takes years of data to get there. Just to show you a sense of the sensitivity of these strain meters, this was an earthquake in the Aleutian Islands back in June or July, I believe it was, that was picked up by these sensors in the subsurface. And so those displacements, the y-axis is on the order of microns, and so they're incredibly sensitive to variability. So are these things sensitive enough to be picking up millimeter scale subsidence rates in the system? Absolutely. They're sensitive enough to be picking up micron scale alterations in the sediments induced by an earthquake that's 12,000 kilometers away. Okay, so I'm going to turn it over to Kathleen.
So I'm Kathleen Jones from the Jet Propulsion Laboratory, one of NASA's facilities. Oops, wrong direction. So I'm going to talk to you about using remote sensing to augment the kinds of work that Tor and Mead have been doing with ground-based instruments to try to get a bigger picture view of what's going on in the coastal Louisiana area. So this, what I consider to be a beautiful picture, is of the Mississippi River, the mouth of the Mississippi River Birdfoot Delta. And that is a radar image. It is not a photograph. And the colors represent different properties of the surface. So in this case, the areas that are darker blue are water. The areas that are very black are still water, and then the shades of pink and brown and green represent different types of vegetation in that area. We're going to be using a different aspect of radar in order to look at subsidence, and I'll talk to you about that next. So we're interested in getting kind of large-scale measurements of the Earth from space using radar remote sensing. And we're going to concentrate on this area that Sam pointed out has experienced such severe land loss since we've been populated this area. There are several areas that are proposed for studies both by the state of Louisiana and that, let me see if I can get my little dot here. This is the Myrtle Grove Subsidence Study Area, and New Orleans is here. So that radar image that I showed before was of the Birdfoot Delta down here. So the technology that we're interested in using is called INSAR, Interferometric Synthetic Aperture Radar. So a satellite flies over, it takes an image, and then whenever it does the repeat orbit, say a week or 2 weeks later, it'll collect a second image looking at the surface from exactly the same geometry. And we can do a comparison of the two images and determine how much the surface of the Earth has moved between those two times. And in this case, those colored fringes represent not elevation fringes, but elevation change fringes. So we're measuring the change in surface position as a function of time between those two images. So we want to use this to measure subsidence in this particular area. And just to show you the strength of this kind of a technology, we used this a few years ago to look at subsidence in the vicinity of New Orleans. And we were able to get high-resolution images of subsidence movement in that area, and we were able to show that subsidence was correlated strongly with groundwater withdrawal from industry along the Mississippi River. And this cone here is more than a kilometer in diameter, and even across the Mississippi River along the Bonnie Carey spillway, we were able to detect subsidence of those blocks that are set into the ground behind the spillway. We don't show it here, but we had some points on the spillway itself and saw that the spillway was not subsiding as fast as these blocks were, probably because the spillway is seated deeper than the blocks. But this gives you information, this kind of information combined with what you know about what the surface conditions are, the geology, the footing of the structures, can allow you to understand the causes of subsidence. And this particular data set was taken with an airborne interferometer, the NASA UAV-SAR instrument. But we're interested now in looking at a bigger picture and using satellites. Today, we have the European Space Agency Sentinel-1 instruments. They have actually two identical instruments in orbit. They image much of the land surface. They have 2 scenes across the Mississippi River Delta that cover from the city of New Orleans south. And they also have, it's very important, a free and open data policy. So the data that they acquire is available for anyone to use. They have about a 65-foot spatial resolution for their instrument, and that is not nearly as high as that airborne instrument that I showed you before, which has about a 1 to 2 meter resolution, so about 3 to 6 feet. But in the future, NASA is going to be launching its own mission at the end of 2021 called the NASA ISRO Synthetic Aperture Radar Mission, or NISAR. It's a joint project between NASA and the Indian Space Research Organization, and it will have the same type of instrument that we had on a UAVSAR, and it will be acquiring data over all land surfaces of the Earth every 12 days with spatial resolution somewhere between 20 and 40 feet. So this is a game changer in what we can do with solid Earth studies, because having that knowledge about what is happening regularly, what is happening with time, allows you to have a better understanding of the causes of subsidence. Is it correlated with groundwater withdrawal? Is it correlated with production? Is it spatially correlated with the depth of the Holocene layer? Yeah, that kinds of information allows you to tease out the causes of subsidence. And that's what we are going to be able to have in a few years with NISAR. And in the meantime, we have the European Space Agency instrument that allows us to get started on these kinds of large-scale imaging from space. And another important thing I want to point out is all of NASA's data is free and open, and so all of this data will be available. So thank you. I think I'll stop here and the moderator will take questions.
All right, now we'll open it up to questions from reporters in the room. Do we have any questions?
Mark Schlefstein with the Times-Picayune here in New Orleans. Okay, so you guys are really talking about how to put together data to help the state of Louisiana deal with the issues that it's facing, and putting in the diversion. The mid-bed area diversion is what I'm looking at from most of these slides. Can you talk about how they would use that data? What is it that they are looking for from you? What questions are they trying to answer?
Yeah. Is it on? Okay. Sorry, Mark. So as I mentioned, that these numerical models that are used to, if we zoom into just the mid-Barrett area diversion, right? And so the models were used for site selection and operation strategies, and for basically the size, how much water you're going to put through them, right? And so you have to feed that to the model. You understand the sediment dynamics in the river and the water and how much sediment's available, and then you put that out in the receiving basins, and the models build land from it, right? And you try and build a diversion both in site and operating strategy that maximizes land building. It's also about preserving existing land, right? Because that's counted on the positive as a balance. And so those models that are used to do that kind of selection and to rate things based on how much land they save or how much land they create, have to have subsidence that goes in the beginning, right? So initially you've got subsidence, a subsidence rate that's relative to that specific area around Myrtle Grove that is the receiving basin for that thing. Well, if you change that subsidence number, that you crank up the subsidence number, the amount of land you're going to build with a given amount of sediment is reduced, right? So that's a very important number that goes into it at the beginning. But what we're saying with the superstation is that there's a secondary effect, that when you start building this thing, the weight of that sediment that's growing out into the basin will deform the underlying sediment to a certain amount. And that's a very hard number to predict. Because we don't have a whole lot of, we know something about the geotechnical properties, and we can take the samples in the lab and we can deform them and those types of things, but there's nothing like a field observation to tell you about how this is deforming. So the idea is the superstation being located within the receiving area, you will be able to compare the predictions about how much loading will cause additional subsidence with an actual observation. So I think that's probably the gist of it.
Okay, do we have any more questions from reporters in the room? Do we have anything on the web chat? No? All right. Okay. Oh, Sid, sorry. Yep.
Hi, Sid Perkins, freelance. You showed a map of coastal Louisiana that has very patchy subsidence, and you also talked about a lot of different factors that feed into that, you know, sediment supply and decomposition and oil and fluid withdrawal. Is it easy to, with the data sites that you have, to be able to parse out the various contributions of each factor at each area or over a small area, or is that something that you can only do after you build up more data over time? Is there a good sense of what's driving various rates in different areas?
Yeah, I'm happy to answer that question. It's a very good question because I didn't really talk about that at all. I was purely talking about what we observe at the land surface, and as you recognize, that's the sum of many different things, and then of course the question arises, what is most important? One of these studies that I mentioned actually was able to demonstrate with, I would say, a pretty high level of confidence that shallow subsidence component, which is really sediment compaction, accounts for somewhere between 60 and 85% of the total. We also know from earlier studies that we've done that what happens in the deeper subsurface is it's there, but it's generally relatively small. So these longer term movements that are also more constant over wider regions, you know, you talk, you know, I would say order of magnitude 1 millimeter per year, which is, you know, significant, but if you compare it to 9 millimeters per year, it's obviously a really, really small component. That said, we still have several variables that are not sufficiently well understood, I think. You know, one I can think of is oil and gas extraction. Kathleen talked about groundwater extraction, which is now being really well documented in these urban areas where the satellite-based techniques or the radar techniques work really well. That's much more challenging in these natural wetlands. Those are the areas where there has been a lot of oil and gas extraction. We don't really have good constraints on, you know, what proportion that has caused to the total subsidence. So there is still plenty of work left to be done in those areas.
I think I could add one thing is that might be obvious, but we didn't say it directly, was that that if, as Tor says, if the compaction of the shallow section is really the big player, and everything up to date seems to suggest that's the case, then what should happen then is, as not just the thickness of that section changes, but also the lithologic character of that, right? The delta is a very heterogeneous place of muds and sands and organic matter, and the mixture of those things has basically results in a different amount of weight per unit section. And so some of that complexity that they may be picking up in those few hundred stations may go back to there's a lithologic complexity in that. in that interval. And so the kinds of things that Kathleen's talking about, where you can overlay a ground subsidence map with sort of a lithological spatial map, then you really have that smoking gun to get a sense of those controls and how sensitive they are to things like lithologic change.
Now, one of the quick follow-ups to that is, once you are able to parse things out and figure out what's driving things in subsidence in various areas, is there any way to solve, air quote, solve the problem other than just adding more sediment and diverting? Is there any way to either ameliorate or alleviate or undo some of these processes, or do you just live with them?
Some of the processes are completely beyond our control. All the deeper crustal stuff, except for deep fluid extraction, of course, but everything else, I don't see any way to, manipulate that. Even the shallow compaction processes, they're going to continue. That there is no doubt about that. The one area where a lot is possible is actually in urban areas like here. New Orleans has subsided tremendously because of artificial drainage, and that is something we see here. We see it in large urban areas around the world in these coastal settings. Many places where it's happening as we speak at really dramatic rates. Those are really things that could be managed, and there is a pretty active conversation here within the city of New Orleans to try to, be more aware of how much, lowering water tables can actually exacerbate things.
Just a quick follow-up to that. There are cases around the world where subsurface fluid extraction was thought to be driving rapid subsidence. The extraction has been either slowed or stopped, and the rate of subsidence has also decelerated. So it's possible.
Yeah, and I would like to say that land building has two components. There's inorganic sediment coming in, and then there's organic, productivity from plants, both above ground and below ground biomass building. So that's another thing that can be done. Thank you.
Yeah, I mean, I'm a geologist, and so and when you study deltas, it's all about the natural processes are about aggradation and decay, right? And when you look at the natural lobes of the delta before we got here, where the river was actively building, we were building new land and elevations were rising, and old lobes that had been, due to river switching, deactivated were in a state of degradation even before we came on the scene. And so in nature, prior to human intervention, it was very much a balance. But even then, we recognized that nature wasn't able to stop the subsidence. It basically caused the decay of lobes after there was a relocation of the river channel. So we're just trying to get back to where we're trying to replicate nature.
Okay, do we have any more questions from reporters in the room? Time for one more.
Hi, Mary Beth with Popular Science. Thank you so much for doing this. I'm curious, you've talked about this as a canary in the coal mine and kind of a warning for other places around the world, and you're talking about, there are lots of other places around the world. Can you tell me a little bit about what other places in the world are kind of dealing with this, and who exactly should be paying attention to this area?
Any of us could attack.
Yeah, sure. Okay. I'll start off. Every major river delta in the world has the potential for experiencing these types of threats. That encompasses about 1 in 14 humans on the face of the earth. So it's a huge population, including developing nations that have dense, like, for example, the country of Bangladesh. The entire country falls within the Ganges-Brahmaputra Delta. And they're experiencing problems similar to this, different because it's a different system. And more broadly, right now we're experiencing relatively high, well, definitely high, relative sea level rise rates along our coastline. And areas that are distant from deltas within the next century may be experiencing the same kinds of rates. So whether it's deltaic or not, depending upon the trajectory of sea level rise acceleration over the next century, any coastal region could potentially be subject to some of these threats.
Yeah, so grab a copy of this, because 100 coastal subsidence experts said that 2 places on Earth are deltas and coastal megacities, because for very different reasons, right? One is sort of a natural sediment compactional processes inherent in sort of the building of deltas. The urban thing is all about fluid withdrawal to support those populations for drinking water, for industrial purposes, drainage, to build. So the Jakartas, the Shanghais, the Dhakas, the Ho Chi Minh cities, these are the places that are experiencing super rapid, rates that dwarf the kinds of things that Tor was showing, where Jakarta rates are up to 1 meter per year of subsidence. And when you're adjacent to the coastline and you're subsiding at that rate and you have 10 million people in your city, it's a huge potential catastrophic problem. And so the real goal of this paper was to sort of say, we really need an integrative approach, and we are a canary because we have altered our sediment supply and we have altered the way the delta works, and so we're experiencing massive wetland loss where coastal subsidence is a major driver of that, indirect, but it's still a driver of it. And so hopefully in some of these developing nations that are either changing the drainage basins of these river deltas or building megacities along the coast and withdrawing massive amounts of fluid, they're going to learn from this experience and not make the mistakes to the degree we did.
Okay, I think that's our time. So thank you very much to our panelists. We'll reconvene in 15 minutes at 2:30 for Hurricanes Part 1. Thank you, guys.
Gotta have 2 studies for hurricanes. Thank you.
Sure, thanks a lot.
Thanks.